This is the walkthrough video for PCTC 2021-2022 round 2 question 11 entering the room. So what we're doing here is we're given a long list of numbers, and as we go through the numbers from left to right, we want to calculate the median of all of the numbers we've seen thus far and add that to our answer, and then print off the answer. So in some ways this question is the opposite of question 10, because question 10 there wasn't much of an algorithm involved. It was more so an implementation challenge of coding 50 or 60 lines of code. Whereas question 11 is the opposite. The implementation isn't too difficult in the sense that our final solution is maybe only going to be 10 to 15 lines of code. But the difficulty lies in the algorithm. Now, if you were to read this question, which you probably have at this point, it seems really easy, right? Like this seems like it should be a question 6 or something, not a question 11. But if you look carefully at the constraints, you see that it says the input will be a maximum of 2 to the power of 20 digits. And also, programs must complete in under 3 seconds. And 2 to the 20 is a huge number. Like, humans cannot comprehend how big that number is. And so we are going to be given some massive inputs. And the website still expects us to still expects our code to run very quickly despite these absolutely behemoth inputs. And so what this suggests to me is we need an efficient solution. We need a solution that can run very fast, even for super large inputs. And that is why this question is difficult. That is the difficulty. You need to find an efficient algorithm. Because if you were just to code kind of the default solution, you'd get something like this. And if we were to submit that, we'd only get 6 out of 10. And if you look at the test cases that we got wrong, we got 4 of them wrong, and it says time limit exceeded. So yeah, our code is too inefficient for the 4 longest test cases. So first I'll just kind of describe the code that I've written here, which is the default solution that you may initially write, and then we'll write the more efficient solution together. So here I've taken in the input and converted it into a list of integers, and then I've also created this function, and this function grabs the median from a list of numbers. So if I just had a list of numbers, this function will return the median number. At least the median according to these rules, because it has a funky quirk thing, which we'll cover later. So the first thing I do with my list of numbers is I'm going to sort them. And to calculate the median, you kind of need a sorted list, right? And it even says in the question, the median is the middle digit when the digits are arranged in ascending order. So when they are sorted, it's the middle digit. So we sort the list, and now we want to grab the middle digit. But the question says, if there are 2 middle digits, rather than using the average of the 2 middles, which is what mathematical convention says, we instead want to only have the lower of the 2 middles. And that means we have to do something a bit funky in our maths. So, as you'd expect with the median, we want the length of the entire list, and we would just divide that by 2. Like we would kind of just have this code where we take the length and divide it by 2. That's going to be our median, and we return the number at that position. But we need a -1 here, because if we had this code, it's always going to select the bigger of the 2 middle numbers. So we need a -1 here to kind of correct for that, so that we select the smaller of the 2 middle numbers. And then of course we do the integer division to figure out how many 2's, well, to essentially chop our length in half, and then we grab the number at the middle position in our sorted list, which is going to be the median. So yeah, that's how you calculate the median in this specific question. Then next, we go through all of the numbers from our input. We calculate the median for all of the from the start to the current number that we are at in our input. So we calculate the median, then we add that to our answer string, and then we print off the answer string. So this is relatively basic, at least as far as question 11 goes. But of course, we saw it only got a 6 out of 10, and we want 10 out of 10. So we're clearly going to have to make this code more efficient. And so let's kind of just delete all of this, except the first line, because that's the input line, which is useful. And we have to have a bit of a think about how we can make this program more efficient. But before we do that, actually, let's first identify why this is inefficient. Why is this so slow? And it's so slow because we're sorting a list. And in coding and computing, whenever you sort a list of numbers, that takes a lot of computational resources. It takes a lot of time and a lot of CPU, a lot of memory to sort a list. Sorting a list is not quick. And so if your list only has like 10 numbers in it, even if it only has 100 numbers in it, that's not too big of a deal. But if our list has like 5 billion numbers in it, sorting it is actually just going to take ages. Like if you were to sort a 5 billion number long list, you are actually just going to be sitting there in front of your computer, watching your computer just wait to try and sort this massive list. And so we want to, if possible, solve this question without ever sorting a list. And so we need to find a way to calculate the median without ever dealing with a sorted list. And I think really there's only one way to solve this, and that's to deal with frequencies. Now, I mean, how many ways are there to calculate a median without sorting a list? Well, cumulative frequency can be useful. So hopefully you've covered this in maths. If not, you may want to pause the video to just go search up what it is. But if you were to store the cumulative frequency of the digits from 0 to 9 in our input, then what we can do is, well, if you visualize it on the graph, the median is in fact just equal to the midway point of the number of digits that we've looked at so far. And so by storing the cumulative frequency, we make calculating the median incredibly easy, because all we have to do is just look at the midpoint. We don't have to bother sorting a list. We just have our frequency list, and then we look at the midpoint of that list, and that's our median. So let's implement that now. Let's create our cumulative frequency list, and that's just going to be a list with a 0 10 times. If you've never seen this notation, what this essentially does is it just creates a list with 10 zeros like that. But this does it in a much faster way to type out. So obviously our cumulative frequency starts off at 0 for every digit, and the way I'm organizing this is I'm going to say that the index represents the digit, and the value at that index represents the cumulative frequency. And that's why I've got 10 zeros, because it's representing the digits 0 to 9. But yeah, now let's build up this cumulative frequency list. So let's go through every number in our nums input list. And so we're going to use enumerate here just because it's a bit cleaner. So we're going to do for index and value in enumerate nums. And if you never come across enumerate, this is just another way of using a for loop to go through a list, except that instead of having just one value here, you have two values. The first value is the index, and the second value is the value, or like the number that's actually at that point in your list. So what do we want to do? The first thing we want to do is update our cumulative frequency list. And so to do that, let's say for I in range value to 10, we want to take our frequency list, look at position I, and increase that by 1. And this is essentially just how we update our cumulative frequency list. So if I'm to print our list and run this code on this example input 48103, we can see our code running and updating our list live. So as it looks at the first number in our input, which is a 4, this is what the list now looks after looking at that first digit in our input. And you can see that index 4 now has a 1 instead of a 0, and everything after that also has a 1, because this is a cumulative frequency. After looking at our next digit in the input, in 8, we see that index 8 now has a 2. We've increased the value of index 8 by 1, and also the value of everything after index 8 by 1. Same thing applies when we look at the next digit 1. We've increased the value of position index 1 by 1, and we've also increased the value of every index after that by 1. And so this is how we build up our cumulative frequency list in Python. Awesome. Let's get rid of that print statement. And so now that we have our cumulative frequency list, let's try and calculate or figure out what the median is from this list. And this is where it gets a bit tricky, because there's some really random nuance to maths that we have to be careful of. Before we do that, let's go through every value in our cumulative frequency list, because we need to compare the mathematical expression that we're going to write to this specific value to figure out what our median is. So let's do for index 1 and value 1 in enumerate frequency. And we want to check to see if the value of the frequency at that point in time is greater than or equal to the median that we're looking for. What's the median? Well, if you go back to this graph that explains what cumulative frequency diagram is, well, in this case, there are 100 elements in this data set, and the median, no, sorry, there are 120 elements in this data set, the y-axis, and the median is at 60. So our cumulative frequency basically just allows us to take the number of data, or the number of data points we have, chop that number in half, so in this case 60, and then look at the cumulative frequency thingy at that point in time to figure out what the median is. And so let's take in the total number of numbers that we have so far. That's going to be indexed from all the way up here. And we want to, well, so actually the total number of numbers that we have so far is equal to index plus 1. But if you remember back to our initial code at the very beginning, because we need to correct for the fact that this asks for the lower middle, if there are two middles, we want to do the actual total minus 1. In this case, the actual total minus 1 is just equal to index. And then what we want to do is we want to, just like we did in our initial code, divide that by 2. But unlike our initial code, we want to also add 1 to this. Now, the reason we want to add 1 is because this value actually represents that if we had a sorted list of all of our numbers like we did initially, this value represents the index at which we would find the median number that we're looking for. But in this question, or in this solution, we don't have a sorted list of numbers. We have a cumulative frequency list. And so this specific index expression is probably not going to work for us. And I guess one way to try and process in your brain why that's true is if you were to consider that we had a list of sorted numbers, the number, like the very first number in that list is index 0, according to Python. The second number in that list is index 1. So the indices in that list start counting from 0. Whereas in this case, you have a cumulative frequency, and cumulative frequencies start counting at 1, right? When we have an element, we start at element 1. And I guess another way to try and digest this weird mathematical expression that we're using here is to say that, right, if we had looked at one number so far, let's say the number we had looked at is 4, then our cumulative frequency list looks like this. And what's the median of the numbers, right? If you only have one number, 4, what's the median of like this set of numbers? Well, the median of 4 is obviously 4. And so we want to try and extract the number 4 from our cumulative frequency list. And well, if we didn't have this plus 1, the value of this is, well, it's 0 integer divided by 2, which is 0. And so the value of this is going to be 0, and therefore our code is going to look at this 0. And that just doesn't make sense, right? Because we're looking at a number that appears 0 times, and we're going to say that the number that appears 0 times is our median, which is just obviously not true, right? The number that appears once is our median. In this case, if we only have one number, the number that appears once is our median, not the number that appears 0 times. Hopefully that made sense. Hopefully that helps you kind of internalize why we need this extra plus 1 in this solution, whereas in the old solution, we didn't have this plus 1. And it's just because we're storing this data, this frequency versus this list of sorted numbers. Like, these are two different ways of storing our input data. Anyway, so if the cumulative frequency at that position is greater than this mathematical expression we just discussed, then the position is the median. So in this case, for example, this would have a value of 1, and this is the first occurrence of a 1 in our cumulative frequency list. And what position is our first occurrence of 1 at? Well, that's position 4, and that is correct, right? 4 is the median of 4. And so our median is index 1. And we want to add our median to an answer string, just like we had in our very first initial code. So let's create an empty string up there on line 5. And then to the string, we can add index 1. But of course, index 1 is still a number, so let's just convert that to a string and then add that to our answer string. And I think that's pretty much it. But one thing that you need to do is break. because as soon as you found your median, you want to stop looking for it. You've already found it. If you don't break, what the code is going to do is it's going to find this one and add that 4 to our answer string. But it's going to keep going. It's going to find another one and be like, ooh, let's add a 5. And another one, ooh, let's add a 6. Another one, let's add a 7. Another one, let's add an 8. Another one, let's add a 9. We don't want it to keep adding these numbers, right? If you go back to our graph, the median exists at this one point in our data. We don't want to add all of the numbers up here as well. We only want to add the number at the median. And so once we found that, let's just break out of our search for the median. And this is pretty much our algorithm done. So if we just print answer, we should hopefully get 10 out of 10. So yeah, this part of the code is where we update the cumulative frequency list. And this part of the code is where we find the median from our cumulative frequency list. And yeah, we got 10 out of 10. We saw that these last 4 test cases, we don't come across a time limit exceeded error. Awesome. But now that begs the question, why is this code faster? Like, we've discussed that sorting is very slow in Python, but in this code, we're still dealing with huge inputs. So why is this code fast? Well, the reason it's fast is because it depends what you're doing. Like how fast a program is depends on what you're doing for every thing in your input. So you want to look at the loops in your program, and the loops in our program is this. Like this is our main loop in the program. And for every digit in our input, what are we doing? Well, we're running another loop, and nested loops are usually very slow. Like this is a big no-no. But in this case, this loop only runs a maximum of 10 times, right? It's capped at 10 because we're dealing with a cumulative frequency list that only has 10 elements in it. We're not dealing with sorting a list that may have a billion elements in it. We're dealing with a cumulative frequency list that has 10 elements. So this is only ever going to run a maximum of 10 times. Very similar logic down here. This is only going to run a maximum of 10 times, because the for loop up here goes through our frequency list. Our frequency list only has 10 digits or 10 elements. And so yeah, for every number in our input, we're only doing basic operations a maximum of 20 times, which is a lot smaller than, say, if we had to sort a list that was 1 billion in length. And so yeah, that's why our code is very quick in this case, and that's what gets us these 10 lovely points. But yeah, I would say general advice for competitive programming is frequencies can be quite useful. If you ever come across a question that looks somewhat like this, where you have huge inputs, and you're kind of dealing with some sort of statistical value or some sort of like value like this, where you're kind of manipulating the numbers, then think about frequencies, because you may not actually need to store every digit. Like if you notice, we're not storing every digit in our input. We're going through the input, but we're not like doing anything to it. In our previous code, from down here, let's just put that to the editor. In our previous code, we were effectively storing all of our digits up until the current point in our input. Whereas in our latest code, we're not doing that. We're only storing 10 numbers at a time. And this idea of a frequency can really help you run these massive inputs in a relatively small amount of time. So yeah, kind of keep this in mind next time you have a massive input and you're stuck trying to optimize your program.